All right, good morning, everybody. I'm just going to share my screen today, partly because I've got Ethernet. One of my students came in and disconnected the Dell and ran the Ethernet cable. So I feel like I've accomplished something already today that's helpful. They're going to try to run one. And the reason I did it is because we're going to play around a little bit with Wireshark today, because your first homework assignment involves getting Wireshark installed and using it a little bit. But I have a whole bunch of other screens up. As you can see, one of the things that's been kind of interesting to try to figure out is how do we get around the fact that none of the federal sites that have all the spectrum data that I usually use are up because of the shutdown. So it's super tough. I can't give you the homework that I had ready because none of the URLs work for the federal sites. So I worked with a guy years ago named Brewster Kale, and he was out of the MIT area, around that area of Boston, and worked on a supercomputer project, and I can't even remember the name now. But we used to meet. I used to go up and have lunch with him in Boston. This was when I worked probably at Rice at the time. I was probably already over at Rice running computing department, not an academic CS department, nothing like that. And he ended up finding his big claim to fame not in supercomputing, but in building something called the Wayback Machine. Has anybody ever watched Rocky and Bullwinkle? Yep, thank gosh. All right. Automatic K. Anyone else? No? So Rocky, yeah, I know. I was like, oh, okay. It's like, hey, Rocky's watching me pull a rabbit out of my hat. Like, so there were these cartoon characters in the 60s that were making fun of the Cold War drama between the United States and Russia. So they had Boris Badenov and Natasha and all this kind of stuff. But Bullwinkle was this moose, and Canadian kind of leaning moose, and big, fun, dumb, happy guy. And he had this super genius little dog friend named Mr. Peabody and Sherman. And they built this machine that would go back in time, and they would tell these like fractured fairy tales, they call them, these old history stories. But the Wayback Machine, I remember when I was a student having a T-shirt with the Wayback Machine, and people would stop me on the side like, oh my God, where did you get that? I got to have one of those. And this is before you could just like find anything you wanted on eBay, right? Anyway, Brewster is of that same generation as me, and so he created this Internet Archive project called the Wayback Machine, because what it does is it crawls around the Internet like Google does, but it keeps everything it finds. And so if you go to that site, and the easiest way to find it is just to go and you can search for Wayback Machine if you want, and it will take you to the Internet Archive. And I've already donated, so you guys can certainly donate if you like, but you don't have to feel compelled. I am one of those people that donates to Wikipedia on a regular basis. Not a ton of money, but like 10, 20 bucks here and there is not going to kill me. And I donate to Brewster's project. So the way this thing basically works is you put in whatever URL you want, and you can put in like Microsoft.com, and it's slow and it's free. Okay. So have you guys ever heard of the Bermuda Triangle of project management? Yeah, some people have. So that's important to bring up here. You'll use this in your career, especially if you have a pushy boss. The Bermuda Triangle of project management is, golly, stop it. Okay, let's try that again. Let me see if I can close these guys up here too. If somebody wants something fast, cheap, and right, they can pick 2 out of the 3, but not all 3. You get to pick the third one. So they can have it fast and cheap, but it won't be right. They can have it fast and right, but it won't be cheap. Or they can have it cheap and right, but it's not going to be fast. It's going to take a while. So you need to remember this. Never let a boss pick all 3. Or it's impossible. You can't do it. Or you'll be working all night long and all weekend and all that, and time to find another job. So on this one, this is right and cheap, therefore it is not fast. So basically what this shows is all of the times they've snapshotted Microsoft.com. And what's kind of fun is to go back Wayback, get it? Wayback Machine, and figure out what things look like long ago, like on October the 20th, 1996. And it's going to pull this up here in a moment, but this is because they don't have enough servers right now. So we just try it again and throw $5 more at them, and it's kind of coin operated, and it's probably also being hacked at all times and stuff like that. So when you get your homework assignment, it's going to require using this site. You are going to have to go to the Wayback Machine to get stuff done, and you're going to have to be patient. So it's going to take you a few extra minutes. So you might want to work with a couple of other people, and whoever grabs it, that's great. So here's what the Microsoft website looked like back then. No fancy graphics, Latin American Internet Explorer race. This is like tech porn to me. I have to click on it now and read, like later today, like what was that all about, and see if I remember it. But you've got interesting design sites as well. You can also go to like newspapers and stuff like that. So if you put something up stupid on the web and you try to get rid of it, you won't be able to, because Brewster's going to catch you. He's going to capture it. So this is used, it's got all kinds of uses, academic, of course, but legal as well. And so if you put stuff up and you think you're going to maybe hide that forever, good luck. In fact, I will also tell you guys, having experienced some of this, in the last 3 years, there have been tools that have been built for network administrators to not capture all the data that's flying around the network, but to just capture the headers. And we'll figure out what IP headers are this semester. But one of the things that you can do a much better job of is, yes? Tons and tons of data. But let's come back to that, because that's sort of where I'm headed, but I got to make sure I come back and loop around to this question, because it's important. No, because early on in every lecture, if somebody raises their hand, it's usually why? It's usually to tell me they're chatting, that they can't hear you. You don't have your microphone turned on, right? So I'm always going to stop in the middle of a sentence, because that's like no lecture. It's the worst of all. I'm also going to bring duct tape and tape those damn doors open, because they keep half of them locked. Okay, so where was I? I forgot. I've lost my train of thought now. And it's not your fault. It's me. Oh, storage. So they have tools that will let you capture the headers of every packet, because one of the things that lets you do a lot better job of is figure out where attacks are coming from. Usually by the time you figure out you're being hacked, the data that would have given you evidence of like how it happened and where it was coming from is long gone. So what network administrators in large companies are already doing, and lots of other places, is they have systems set aside to do nothing but capture all the IP header packets. Think about that for a minute. All of them. Every frickin' one. Into and out of your network. Forever. So it's kind of like a Wayback Machine in a way. So if you need to go back 6 months and figure out where was this software first installed from, what were the IP addresses of the places that were doing it, what protocol were they using, you can't have the contents of the packet, because those can be orders of magnitude larger than the headers, but having the headers is enough to figure out where to place the blame. So that is now common business practice, to have systems that capture all IP headers. You need to remember this. This is important. So if somebody is trying to prove that you did something, it's not a problem. So when I worked at Cisco, we shipped systems with a company called NetApp. And my partner, who I worked with, he had another large storage vendor, EMC, which is now part of Dell. And they are two of the large dominant storage providers. So in business with storage, you'll have these big, massive cabinets with thousands or hundreds of drives, each of which is lots of gig. And so all of your servers in a data center will typically share one of these big storage arrays, and you have lots of them. So the storage is massive. And we used to ship these things all over the world, but whenever a government with an agency with a 3-letter acronym wanted to buy those, They would go through a contractor, a federal contractor, and they would order everything they needed for them, but never disclose their name. So when it would show up in my sales list at the end of the month, it would say protected party or words to that effect, which basically meant legally you have to assign the warranty and things like that to the ultimate customer, because to buy it and then try to resell it to someone else, unless you are set up as an authorized reseller legally, you cannot pass the warranty along. So if with a car, it's different. You know, cars have warranties specifically that will allow you to pass the warranty on to someone else. But let's say you open up a store and you buy Apple computers, and then you fly to Mexico and you sell them there to people. The warranty will not extend because you've broken the law by, or at least violated the contract. So it's a tricky situation when a three-letter government agency wants to buy equipment, because they do expect for the warranty to happen. And so you can tell how much they're buying just by looking at protected party. And they were always our biggest customer. So my guess is the NSA is buying, and you know, we also talk to people that work at these companies. They buy truckloads of storage every month. So what do you suppose they're putting on all that storage? I mean, they're buying like 10 times as what General Electric buys, or 50 times what, you know, some other large corporations. What do you think they're putting on all that stuff? Everything you're doing is what's going on there. After 9/11, lots of stuff changed. So back to your question about way back. One of the things that Google has to do is set up a budget every year. And what do you suppose the person who is sort of figuring out their budget for the year for Google email, Gmail, what do you suppose they write down in their budget for how much it's going to cost Google to buy all the storage that they need for Gmail every year? Take a guess. It may not be the answer you think. What do you think they spend on? What do you think they consider the impact financially to that company to be every year from buying all that storage? Take a guess. I don't expect you guys to know the stuff I'm trying to teach you. If you already knew it, you wouldn't need to take the class. And I will never embarrass you. I make a fool out of myself. I have the corner on the market in here. I'm the fool, not you. So throw out a number. Here, you ask the question, you throw one out. 1,000? Cheap? So he's in the right direction, not cheap enough. What do you think they budget for it? Too much? Less? Much less. No, less. Free. 0. How can they do that? Those discs aren't free, but they are now. So what pays for that storage? The ads that you see. So they figured out a business model where it actually doesn't cost them anything to store your stuff. So as a result, they never have to throw anything away. In fact, at Google, there have been at times, I don't know if it's still the case, signs up that say, throw away nothing. In other words, keep everything forever. So there are models that work in this industry that allow you to store everything you need forever and ever. So you can get away with this if you have some modest amount of support. If you have ads, for example, that's one model to pay for the stuff. And the cost of the drives is almost nothing. I mean, think about it. You guys have Gmail or Hotmail or some other variant, probably. You ever done a search for email and seen the messages that come back from like 2 years ago and 3 years ago and 5 years ago? Do you wait 10 minutes for someone to load a tape onto a tape drive and pull that 10-year-old email up, or does it come up instantly? How? How do they pull that off? How do they have everyone's emails from 10 years ago sitting on a drive with electricity, running, spinning, for years and years, waiting for you to search for that word that pulls something up from 2008? How can they pull it off? They figured out a plausible business model to make that happen. So once you've broken through that barrier, then the assumptions you have that what like deleting something means changes forever. Good luck deleting something. Yeah.
How does Wayback
So Wayback has donations that they get from people, and knowing Brewster's very persuasive. I have no doubt Brewster has approached every large, massive storage consumer like Google, and basically has guilted them into letting him rent storage at the same incremental rate that they pay for themselves. So if besides having a business model that works, they also are the world's largest consumer that's not protected party. And so they probably pay less for everything than everyone else. So if Brewster comes in and says, I'm a poor, starving student on a fixed income, help me, Father, it's for the children. And, you know, he's a super smart, very nice, gregarious guy. I mean, if one of these days I need to call him and ask him, like, come give a guest lecture online. So, in fact, you've given me the idea. I may talk to him. I was just chatting with somebody on his staff a couple of weeks ago because they accidentally sent out a second email to people asking for money that had already just donated, and I wrote back and said, don't you ever apologize for asking for money. You got to hit people up constantly, and plus it's for Brewster. And so she's like, oh, thank you, Brewster's great, you know. So I need to reach out to him and say something anyway, because a friend of his died not long ago, so I also need to let him know about that. So that's archive.org. So a couple of things I will give you an assignment that has URLs that will come up at archive.org. And some of the stuff I was very surprised to see. This is the government's website, and when I tried to pull this up on archive, it said, but wait, this is already available still on the internet. Why don't you just go look there first, idiot? And so I did, and I will give you one. But do you remember the map I showed you last time with the spectrum? So this is a way to drill down officially and then pull up reports on specific parts of that spectrum. So if I want to pull up, and just did, pull up a little text report. Let me move my picture up a little bit here. This is a bug. Every time I try to capture this bug in WebEx, I can never do it. Okay, so here's a report on what's being used for this range of frequencies. Basically government policy from an FCC administrator on what's it assigned for, the number of licenses that are active in each of these areas, how it's distributed. And this is just, you know, cranked out in bulk because there's thousands and thousands of these little, at least 1,000 of these things. And so they have a database. This is not an exhaustive list of who actually has the licenses. This is a policy document that says the government set aside use for these policies. So when you get together in these international meetings, this is something you hammer out with other people. What do you guys use the spectrum for? Well, we use it for buoys in the ocean to kind of let us know about wind speeds for kind of hurricanes and ship navigation systems. Well, we use ours for amateur RF control of like airplanes, like these model airplanes people fly around the big parking lots and stuff. Oh, we use them for drones, you know. So you have to kind of hammer those things out. All right, enough wandering around. And I mix a lot of these side stories. None of the stuff we talked about today is in the book. So I try to mix in lots of practical things that make this career a little more fun, make it interesting, and tie you guys to what's really going on in the world. We will cover all the theory that you need in the class. But some classes I've seen like this, they send you to lab and they teach you how to plug cables into routers or how to build an Ethernet cable. That's the day I quit. We will not be doing that in here. You know, first of all, most of you, if that's what you want to do, I couldn't begin to teach you how to do it because the contractors that we used to hire, you know, it's just like everything else, right? So I have this debate with people in Mexico all the time. Americans that come down and visit Mexico and they comment on the quality of construction not being all that great. And they challenge me on like, why do you think we should still have this work program that allows workers from Mexico to come and help us build things here if, you know, I mean, look at the quality of the construction, because that's all the people that know exactly what they're doing are in the U.S. already. If you get good at doing it, the market you want to do it in is here. You get paid a lot more for it. So the ones that are left behind are the ones that aren't as good. So do you not get that? So the same is going to be true here. If you want to end up working hands-on, building cable harnesses and wiring, stuff like that, that stuff is a work of art. Those guys are, the word we spoke earlier before everybody else came in, starts with CH. So anyway, she knows what I'm talking about. It's the word in, right, but yeah, she got it. It's not the best word to use, but it means somebody who's like really good at what they're doing. So I'll try to find you guys some pictures. We may run into them sometimes about the type of job that good contractors do with these cabling systems. And it's like a work of art. It's unbelievable to call it. I couldn't begin to show you how to do something like that. I am nowhere near good enough to pull something like that off. So what we'll focus on for side things are things that are usually online and things that are fun that might matter to you. So we talked a little bit about this protocol before we dove off on another chapter last time. And so what I want to do is finish that side trip that we made, which is, where did it disappear to? How interesting. Did I pull it up over here? No, it shut. Why did it do that? How did it close? Okay, let me open it up again. I accidentally closed it right before we started here. I had it up before class. Okay. It's funny, it came up right to the slide. Okay, so this is the path that an RFC will take to get to a standard. So a lot of the stuff we've talked about today are based on two kinds of standards: communication protocols, which govern how we talk to each other, and we're going to look at lots of examples of those this semester. So this would be like, if I walk into the room, am I supposed to stick my hand out? So just imagine a president of the United States meeting the Queen of England, because we mess up something about that all the time, and it always shows up in the news. You know, you don't walk in and pat her on the back, for example. We've learned that. Okay, that's a no-no. So there's rules about how to do it. And believe it or not, there's protocol diplomats that sit down with their counterparts ahead of time, and they line out exactly what's going to happen. Who's going to sit down first? When do you stand up? When you sit down? When do you pull the napkin out? You know, you think the rules that mom tried to teach you about which fork to use are bad? Nothing. So there are communications versions of those as well. How does a browser talk to a web server? How does an email client talk to an email server? And how does TCP establish a connection to another server, et cetera, et cetera? The other types of things that typically end up in standards that are required are more of behavior technology standards, things that can be policy, for example, such as how do you check to make sure an email is from a bona fide email server for a domain that it claims to be from before you actually accept the email. So just because you get a well-formed, proper protocol message that says, I'm an email message from NewYorkTimes.com, did it really come from the server that is supposed to be handling email from that domain? And how do you check? And what do you do if it isn't? So that was a big spam reduction. That ended up as something that can be published in an RFC. So anyone can publish an RFC at any time they want. You can throw it out there. It'll go nowhere. So think of this more like a political campaign. There is voting, as you can see in here. 6 months and 2 tries, 4 months and 2 tries to get people to agree to move your standard along towards the official internet standard goal line. That's the touchdown. That's where you're trying to get. So usually the organization that is sort of running the show, the Internet Engineering Task Force, or just the IETF as it's called, they see well in advance when something's needed. And they will go to their members and try to find out who's good at this already, who's already looking into this, who knows about it. Let's get you and a couple of other people from other places, and we need you guys to try to write a document for us. Put something together. Bring us a proposal in writing as a paper, and let's talk about it. We'll bring it up at one of the IETF meetings. I have one coming up in June. Do you think you can have it done by then? So what this working group leader will do is then try to go around to other people in the working group and say, look, this is what you guys talked about. We're going to try to get this done. They're going to bring it up for us in June. If you have any input, if you have any questions, work with them now, because when this thing comes up, I'm expecting a positive vote from you. We need your support to do it, or we're not going to make it past this hurdle. Once it passes one hurdle, it'll go to a larger group. And at this point, it's like a political campaign. You're trying to get a mayor to agree to run for office, and you're trying to get business people to agree they'll support them and they'll be behind them, et cetera, et cetera. Okay, so it's somewhat similar to that type of system. Once it becomes a standard, it can become a standard in one of 5 areas. The ones that are required means everyone on Earth must conform to it. So if it's a change in standard that affects routers, it's possible that every router vendor will have to change their code and everyone will have to implement it around the world. That's on the internet. There are tons of routers inside institutions, like inside of U of H, that may not have to be touched. But the one that sits at the edge that sends packets out to the internet would. At least on that interface, it would have to run. So you might have a router that's running more than one set of code. One that faces inside and one that faces outside. Right? Make sense? Okay. So I may have time to give you guys an assignment to kind of go find a couple of these, just so you know where to go look to get it done. Okay, so that's the slides that we were in the middle of last time when we ended, because we had just finished looking at this one. And we had talked about NAPs and IXCs and that kind of stuff. Okay, so back to the slides for our book. What we're going to do now is look a little deeper into the core of the network. And so you'll notice, let me make this full screen here. That's not the right one. Let's try this button. I've only used Macs for 15 years. You think I know the buttons. Actually, I've used Macs now. I don't want to do that math. It's too early. It's too long. It's over 30 years. So you'll notice this area is highlighted on the right. This is meant to represent the core. One of the things you'll notice is there is no end systems connected to this. So philosophically, when you're designing these networks, that's a safe bet. In fact, there probably are end systems connected to these things to let their network administrators log in and do stuff like that. But as for the purposes of our course and purposes of understanding that there is a dichotomy between the systems at the core and the routers at the edge, we will go ahead and play along with this fantasy that these are purely there to exchange traffic with each other and not ever to talk about the computers and the servers at the edge. So for the network, everything at the edge is just hanging off at the end. It's like a piece of fruit. It's all in systems, whether they're in a Google data center and they're big, massive CPUs, or if it's a tablet. It doesn't make any difference. So these boxes are technically forwarding packets. They receive a packet, they look at its destination address, and they make a decision among all of the output ports, all the networks that they're plugged into, connecting together, which one is probably the best one to send it to next. They know it can't come from the one it went to, so if that's the decision they make, like the best place for it to go is where it came from, then they do nothing with it. And that happens. You have a router that sits on a LAN. It's going to see a copy of every packet that anyone on the LAN generates. So if I'm sending something to you, and we're both sitting here on Wi-Fi together, but we're running like a little chat thing that works, the Wi-Fi router will see every one of those. It will forward none of them out to U of H's backbone, because it knows the best route for that packet is already on the same network, so it just doesn't do anything with them. We don't need it to. So that happens all the time, but usually routers need to forward packets. And your router at home forwards them all to the same place. There's only one outside world connection you usually have at home, and that's the cable modem or high-speed internet connection you've got from the phone company. But every single packet still gets looked at, still gets dutifully looked up in a table, and it goes, where shall I send this one? And you're like, come on, are you kidding me? It's like always the same answer, just send it out to the wire. But that's the protocol. And we'll talk about sort of why that is. Okay. Packet switching, therefore, is a store and forward network. This is a really important concept. With a telephone call, if I digitize your voice 64,000 times, 64,000 bits a second, and I'm capturing it 8,000 times a second with 8 bits each, I can send those bits as I capture them. Just a stream of bits one at a time. I do not need to compile a bunch of them together in a group and wait until I have, let's say, 100 bytes worth, and then put an address on it and send it to the other end, because with something like a telephone network, It's a dedicated point-to-point circuit. So we talked a little bit about circuits, and we'll talk a little bit more about them. But a dedicated point-to-point circuit basically suggests that there's no sharing of this network with anyone else. Everything you drop on the wire is always going to go to one place. It's like a printer cable. I mean, where else would it go? You know, you plug it in directly, and there's only one possible destination. So the phone network creates that illusion for you every time you make a phone call. You don't have to worry about putting an address on every packet or doing any of that. It's as if you pour bits in and they only come out at one point. Whenever a network is shared, however, then you need to go through what the Postal Service goes through. You need to gather some information together, put it in an envelope, put an address on it, and drop it in the mail. So that it's going to get mixed. You know it's going to get mixed with lots of other people's packets, and you need it to be able to make its way to the end. So there'll be a postal worker who looks at each envelope and makes a decision about which mail bag it needs to go in next, one by one by one. So whenever that happens, you generally have what's called a store and forward network. So specifically for a router, what this means is the bits are sent at near light speed over whatever the communication media is. The bandwidth of the network dictates a measurement for how many seconds it's going to take to transmit all of your bits that are in your packet onto the wire from the time you first start sending the first bit to when the last bit is on the wire. Now the packet has completely left your computer. That's the time it takes to actually transmit the packet onto the wire, known as transmission time, and it's directly affected by the bandwidth of the network. But once it starts flying over, it's very possible you could still be transmitting bits that are remaining on your computer still. You haven't gotten them all on the network, and the first bits are already arriving at the router, at the other end of the connection. So what's the router supposed to do with these bits as they're arriving? Is it supposed to just continue to send them on? No. It needs to wait till all of the bits arrive for that whole packet. It reconstructs the packet. It does things that are very important, like check error correction codes, make sure it wasn't corrupted. The address, it needs to get a substantial part of the packet in to look at the address. At least it's at the beginning. So that's a help. But you've got to wait for the whole thing to get there. So there's delay caused by transmission delay. And each device along the way has to wait for the packet to completely arrive before it can start sending things along again. That does not happen on a circuit switch network. A circuit switch network sets all that stuff up ahead of time. It doesn't need to look at anything in the packet to figure out where it needs to go. It's already nailed up the connection, and it already has hooked up all the wires, virtually speaking, from end to end. So as the bits arrive, they just flow all the way through all the intermediate devices, all the way to the ultimate final destination in the other part of the world. So think about a phone call from here to Germany. It certainly goes through lots and lots of telephone company switching equipment, but none of it stops any of those bits. None of it waits to collect the bits to see where it's going. None of them grabs them as packets, at least not as far as you can notice. So what's happened in the industry is both sides, the circuit switch world and the packet switch world, have done a lot of interesting things in the last 40 years to learn from each other and to kind of each go in the opposite direction. And I'll point out some examples during the semester, but one that's relevant right now is, as you know, when you listen to like streaming radio or you're watching live video feeds, that stuff was invented to run on a circuit switch network. Television channels and radio stations, they didn't have IP addresses. They didn't have routers. You broadcast radio, you tuned it in, and it comes right there. So if we're going to try and let you now listen to radio and listen to television on the internet, which everyone does, right, from iTunes to SoundHound to CNN to whatever, of course that's a packet switch network. So how did they do it? They keep the packets small so that there's very little delay, and so little that you don't notice. So if the size of the packet is small enough, then as the bits start arriving, yeah, it's a store and forward network, but it doesn't take but a millisecond for me to get the packet. I have the whole packet in and I send it on. So it's going to be lots of small packets instead of very few large packets. So it's a little less efficient, but it's faster. Make sense? At the toll road, anybody drive through toll gates and stuff like that? Would you rather be behind a truck or a car? It's the same person taking the money. It's the same human being. Anybody can drive, either one. You've got the license to do it. Doesn't take any longer for a truck driver to reach their arm out the window and hand the money than it does a car driver. But why would you rather be behind a car than a truck at the toll booth? Yeah, once it's cleared, it's able to clear the toll booth faster. It takes longer for that whole truck to make it all the way through and the gate to go back down and for it to be your turn. Right? That's an analogy for here. Right? So bigger packets are going to have to wait longer to get there. And if you are a small packet, you do not want to be on a congested network behind big packets. You'll end up delaying. So routers also may need to do things like not just store and forward, but prioritize a little bit as well. So the entire packet must arrive. So let's take a look at an example. If I have a 7.5 million bits per second network, which we normally write down as 7.5 capital Mbps, megabits per second, we wouldn't usually write it down the way you see it here. And let me get myself a little scratch pad space so I can annotate a little better. So you'd write it down as that, right? And your that's the size. Oh, I misspoke. That's the size of the packet, isn't it? That's the size of the packet. So that is correct for the size of the packet. And the rate at which you can send things is 1.5 million bits per second. So you basically are going to require 5 seconds to get that packet transmitted. And once it arrives at the router, if it's got another set of transmissions to go, then it's going to be twice that amount of delay. So when we start measuring delay over networks, one of the things I'm going to recommend to you guys is that you pick a point to start measuring transmission delay. And the transmission delay starts when the very first bit begins its journey over the network, but you still have lots more bits behind it, and you need to count this entire amount. It's also true that it takes the same amount of time for the bits to all arrive over here, and you could count this amount of time as well. Don't. Count one or the other. Do not count both. So if you're going to count the amount of time it takes for this packet to arrive, what you traditionally will do is count how long it takes for the entire packet to be transmitted and set that aside as transmission time. Then you will count how long it takes for one bit, the lead dog, the bit in the front, and you will follow it the rest of the way and ignore all the rest. You will follow this and figure out how long it takes it to propagate. That's a factor of the length of the network only. It all travels at near the speed of light. It doesn't matter how long this took. Once a bit's on here, it's traveling over wire. You know, God doesn't care what kind of computer you have. Copper is copper. The electrons aren't going to change just because you paid more for the service this month than someone else. So the transmission speed's going to be the same. So it's a factor of length. And then once it arrives here, so you can call that propagation delay. And then once it arrives at the router's got to inspect the packet and look at it. And so there may be some time for it to process what's going on. There also may be a delay. There may be packets coming in from lots of other places, and there's this big long queue waiting to get on this line. So you may have a queuing delay, a wait. And then those are the factors that you're going to deal with. Sometimes people will just call this, you know, the time spent in a router, because it's a combination of the two. And then you start it over again. Transmission, propagation, and it's here. Transmission, propagation. You do not count the time it takes to arrive until the last bit. Count it once. We'll go through lots of examples. All right, so I'll just point that out now, and then we'll come back around to it again. Okay. So here's queuing delay and loss, so a little bit more on it right now. So let me make this a little bit bigger again. So here I have 5 computers, 2 on the left, 3 on the right. There's 3 routers, and this network is running at 100 million bits per second. So if I have a megabit packet, it's going to take 1 second to send. If I have a megabyte packet, it's going to take 8 seconds because a byte is 8 bits. Transmission speeds are always expressed in bits, and sizes of packets are almost always expressed in bytes. Don't forget the 8. Always remember to use that factor. So here I've got blue and red to denote the packets that are arriving from these two systems. They will get blended together by the router, usually first come, first serve, unless you go to the trouble of doing something different. And this has to have memory in it. There's an RFC for that. There's an internet standard that says, here's how much buffer memory you must build in your router that statistically will handle enough packets that you will not end up filling your buffer so often and dropping packets when it gets full and you just can't take anymore. Like, I don't know what you want me to do. You're sending me bits. I don't have any room for them. We're just going to pretend you didn't do it. I'm going to throw them on the floor. So that happens all the time when router buffers get full. So there's a standard to help guide router manufacturers on how much memory do you need. They can't put in an infinite amount of memory. But the problem they're trying to solve is dealing with this situation. If the arrival rate in bits exceeds the transmission rate for a period of time, packets will queue, waiting to be transmitted, and then they can be dropped. And because packets arrive stochastically at random intervals, it's not the case that you won't drop packets even if on average the rates match exactly. So even if you have a network where the arrival rate matches the transmission rate exactly, you will still have packets get dropped, you will still have buffers that get full just because of the randomness of it. So let me see if I can show you an example. Let's see here. I think this is the one I want. Yep. So I told you there were lots of animations offered by the book. So let's just start one up. Okay, so here's packets that are being sent. They don't speed up as they go along, as it's showing here. That's just to make it look sexy, I guess. And what they're showing is that the packets are arriving 500 packets a second. It's not the same measure we would use, but just to keep it simple. And the network that they are being transmitted on by this router in the middle, which is what this is 1,000 packets per second. No problem. Nothing ever gets delayed. Nothing ever waits. So what happens if I speed this up a little bit, or better yet, slow this one down a little bit? Actually, let's make it really obvious at first and start it up again. So now they're coming at me fast, and I'm trying to send them out a network that's slower. This happens all the time. Not everybody in the world buys the same speed of network. You know, this is like between your house and the rest of the world. However fast your network is, it's not as fast as the core. So when you're sending things here, they're going to queue up, and the colors show you that as soon as the pink one, then the buffer gets smaller. But you can see what's happening here. What's happening? It's filling up. So what's going to happen when it gets full? You're going to drop. So you can either set rules for how that happens, or just let it happen randomly. So you can process the packet, let it come in the door, and just drop it before it heads out. But there's a much more intelligent way to handle this that we'll talk about. It has to do with fairness in processing. Usually routers are completely panicked, strung out, operating at full capacity all the time. One reason for that is that's exactly what the network manager wants. If you spend $100,000 a month on a 10 gig network, fiber ring, to connect two sites together, and you're not keeping the network full, expect your boss to ask you why. Well, because I don't want to run the router and belong beyond 80%. I don't give a crap about the router. I'm paying $100,000 a month for this thing. Push the packets over. So good network practice is to run all of your networks completely full all the time. It sounds counterintuitive, but if you were a traffic engineer, if you were applying for a job as a traffic engineer, and I found out you were a network manager before, we would have to have a talk, because I don't want you running my roads the way you ran your network. or else it'd be traffic jams 100% of the time, completely full. But that's the most efficient way to do it, isn't it? Right? So isn't that what airlines do with seat pricing to get you to fly on the less popular days so they can fill more seats, spread out the demand? All right, so this is obvious, right? It's too slow. What's going to happen if it's matched? So packets are not sent at perfectly even intervals. That doesn't happen. If you're sending a radio broadcast, then yeah, you're going to create a packet every 10 milliseconds, every 20 milliseconds, and send it just like clockwork. But as soon as your traffic gets mixed with somebody else's, it's not going to happen. So math will prove, the statistics show, that even if the rate comes in at the same time like that, it's still gonna queue up. So it's kind of interesting. So you've got rules for how this happens. Fortunately, typical routers don't look like this. Why isn't this the way everything works? Well, if the only thing this router were doing in its whole life was connecting these two things together, then I would ask you, why do you need the router? So what might typically be the case that you would expect to see is you have a router here with maybe 3 connections, and traffic can go in either, any direction you want at any given time. But if we're going to focus on this one, you may have 3 different connections. Some of this traffic needs to go here, some needs to go here, and you hope that it averages out. If the router can't handle the traffic on a sustained basis, for these guys, it's the job of these routers to figure that out and to change their mind about where they want to send the stuff. So maybe this router also has a connection. There's another way to get to the destination over here, and he'll instead change his mind and start sending his packets this way and not send them this way anymore. And so now there's a little less competition for what these guys were trying to use it for. So routers are figuring this out dynamically all the time. You can hard code a route that you require that a router use to remove its ability to do that, but generally you want them to be able to pull something like that off. Okay, one other animation that we can take a look at that we've talked about is transmission versus propagation delay. So let's suppose we have a 10-kilometer long network that's sending things at 512,000 bits per second with 100 byte packets. So let's see what happens. So what do you notice that's happening here? What happened? When the first bit was being transmitted, by the time it arrived at the far end, was I still sending bits? Yeah, so my packet took longer to transmit than my bits took to propagate. Did you see that? That's why the whole thing turned red and stayed red for a while. I'm still transmitting, but packets are arriving over here, and if you watch, the tail end of this thing will come flying by, and there it is. It doesn't have to always be that way. You can have a network that can be much faster. It doesn't take as long for you to get all the bits on the wire. That's all it means. It doesn't change the speed at which the bits travel the network. What do you think will happen this time? What will it look like now? Yeah, it'll look like a snake that swallowed a mouse. It'll just be a bump that moves along. Let's see. Not quite fast enough. Let's try a little bit faster. Yeah, see? So the whole packet, from the beginning to the end, existed on the network. It had left the sender completely, and it was out in the ether somewhere. And it hadn't arrived yet at the destination. It may need to go through lots of other devices in the middle. We could also make this network much longer and make that a lot easier to spot. Do you see the little red line going across? Yeah. So this is something that we'll look at with lots of models to figure out, okay, this is too easy, just one packet. I mean, come on. This is when your boss would yell at you. What are you doing? Do you like working here? Is this the career you want? Are you enjoying this? Do you like me? Have I done something to upset you? It's one of those kinds of talks. Okay, so packets will be queued and packets will be lost if things get full. So a couple of key functions that we're talking about here. One of them is the actual forwarding of the packets. Taking the bits, queuing them up as they arrive, getting the packet put back together, and then sending it across some type of electronic switching fabric to get it into memory at the front of another communications link and then back out the door. So the electronics of dealing with that, of watching the sinusoidal signals coming in, deciding whether they're ones or zeros, depends completely on the encoding mechanism. So it's different on Wi-Fi than it is on 10 megabits Ethernet, than it is on SONET, than it is on different type of DSL line. All of them use different electrical encoding schemes. So you're going to have a card in the router that knows how to speak whatever encoding language is arriving on that specific communications link. If you have 10 different links, you're going to have 10 different Ethernet cards, 10 different Wi-Fi cards, or some mixture of them. So you can encode them to turn them just back into binary data, ones and zeros. So now you've got it in. Now that you've got it, you can look at the address, the destination address, and somebody needs to make a decision about where to send it next. That's the second thing the router does, which is actually the routing. And that's where the routing algorithm comes in. So as the packet arrives, as soon as we have a view of the address, the destination address, which fortunately is near the beginning of the packet, so even if there's tons of bits arriving, we're going to see in the first few bits the address, and we can begin work right then on figuring out where it needs to go. We don't know if the whole packet's going to arrive. We don't know if it's corrupted. Of course, it'll get thrown out if it is, and it won't have made any difference. But assuming that most of the time the packets arrive correctly, as the address arrives, we can then begin the task of looking to see where we think it needs to go, telling the switching fabric, I need a path from me to this other card, and the switching fabric will signal you when it's ready, and you can ship the bits across and get them in the memory queue for that other transmission link. So that's going on. Those are two separate things, completely different. In fact, it's such an issue, the speed of this is so important now that you'll see as we get to routers, we don't really even have time anymore to do anything in software. So in the beginning, with the early Cisco routers, which I had the very first model Cisco router on my desk, and had I bought stock in the company instead of whatever I wasted my money on at that time, we would be having this conversation from my ranch or my yacht or something like that. Okay, so the very first Cisco router was just a Unix machine. In fact, they all run Red Hat Linux today. All of these networking devices, pretty much around the world, from pretty much all manufacturers. So it's just a computer. It just happens to have a lot more cards in it than yours. So it may have 100 cards in it or 20 cards. So chassis is a little different. But it's running Linux. It's running an Intel chip just like yours. It's exactly like yours. They may have some tweaks they made, but it's basically an Intel microprocessor. And they write software to run on it. Maybe in C, maybe in something else. So this routing algorithm is a C program running on Linux on a PC. Well, can't you do that? Can't you run a C program on Linux on an Intel-based system? Sure you can. So one of the ways you can emulate what a router does is just use your laptop. In fact, there's a really good network simulator that's gaining a lot of fans around the world. It's open source, so of course it starts with G, right? G Network Simulator 3. It's worth checking out, and we may take a look at it at some point. GNS3 is pretty powerful. What it is a set of programs that emulate what a router would do. And it's an environment that lets you build a fake network in memory and then run algorithms between them. The thing that's kind of mind-blowing about it is they have successfully implemented a layer of software that allows you, with permission from the vendors, to download the actual copies of software from vendors like Cisco that would normally run on their hardware and instead run on top of this. The actual block of code. You have to have a Cisco license, but if you're running Cisco routers, you have one. So you can download it, and emulate exactly your router or your switch or whatever piece of equipment and build a network completely in software that's got the same number of devices that you have, running the same versions of software that you have, with the same amounts of virtual memory that you physically have real memory in your system and all that, and you can simulate your network in here. This is how troubleshooting is done in the industry. When you call Cisco Technical Assistance Center, it's answered by an engineer, typically in Mexico City, and they will run software that will collect all those details about your network and then instantly reproduce it in a Cisco data center using an approach similar to this. So they can reproduce the bug that you're trying to. Probably you don't want them trying to reproduce it on your network if the bug was something that crashed your network, for example. Okay, so we can do that as well, and I've begun the journey to develop new labs to do kind of more and more of this stuff. All right, so that's what's going on inside these routing algorithms. My point of bringing GNS3 up is once you pull this software that makes these routing decisions into an Intel server running in a data center somewhere, then why can't I really do that? Why can't I do that over here? Why do I need every one of these things to be a full Linux system running C programs? Yeah, okay, I need the electronic fabric part of it to physically like receives the bits and then moves them across wire into a memory queue for another. But the part about deciding which output queue it needs to go to or whether I want to route it at all, why do I need every router to run that software? It's like Waze. You know, you can just run it in one place in a data center and update as you see things changing on your network. You can tell routers different things you want them to do. You know, I want you to now take a left. The wind, just like air traffic control. They look at the weather and the landing strips and all that stuff, and they make decisions over the entire network. No individual airport has to know everything going on in the world. And with routers, they can't. So the problem here is the network's too big. Routers can't make the best decision where to route. You know, I keep saying they make a pretty good decision about where to send the packet. Well, what if you wanted better than that? We've never been able to do it. But we can see how we can. And we are moving in that direction. So we'll have a chapter that talks about that in the book. That's why the 7th edition is required and not just the 6th edition. So as I mentioned, circuit switching is different. And you can emulate circuit switching on a packet switch network. We all know this because we can listen to streaming radio. And whenever you're listening to streaming radio and it pauses for a minute and you see it says buffering or whatever, that's when it's not doing a great job of emulating a circuit switch network. That's when it's, you know, the fantasy's caught up with it. It's having to deal with delay and stuff like that. So when you watch Netflix, anybody here watch Netflix? So what happens when you first decide you want to watch a movie at Netflix and you hit the button? I don't use Netflix very much, so it's a genuine question. What's the very first thing that happens after that? Well, I mean, like, what do you see on your screen? Does it show you a Netflix logo? Is it animated? It is with Prime Video from Amazon. When you decide you want to watch a movie, there's a little Amazon Prime logo that might animate and roll in and takes 3 or 4 seconds and all that. What are they really doing during that time? Buffering. They're faking you out. They don't want you to hit refresh. So they're playing something pretty with colors and blinking lights to entertain you for a minute. But that is coming from firmware on the device. It's pre-stored. Or it's a little movie that they stored with the software. Because while they're doing that, they are rushing to get the packets to your system. Netflix uses some other crazy tricks that we'll talk about in pretty much in depth this semester as well, that keeps that little buffering wheel that we talked about with radio from happening very often. You don't usually see that with Netflix as frequently as you do with other types of streaming services. Why? We'll talk about exactly why. So in this case, what I'm trying to do is run some protocol between these two sites that is trying to implement a communication scheme that is very intolerant of delay, and it's also very intolerant of packets arriving spaced apart differently from each other. You know, with a television broadcast or a radio broadcast, I mean, it's like a beating drum. You need a packet. You can predict you're going to be generating a packet like every millisecond or every 10 milliseconds or something like that. Like clockwork. It's never going to change. So you want them, you want the network to take them and send them. You don't need it to be slowing some down. So if I drew out how I wanted them to look, do you remember the network we saw a minute ago where that little packet in red that we saw was just a little sliver here? Remember that? If I took a snapshot of what I would like to have a radio transmission across the internet look like, I would like it to look like this. I would not like it to look like this. But that's how it looks. So if I'm going to do a good job of emulating circuit switch, I need the packets to be very regularly spaced apart from each other. And if I do a good job of it, then I'm said to have successfully emulated. There are technologies, network technologies, that are really good at doing this. And sometimes they're used by the telephone companies because now what they want to do is build one network for everything. When your voice packets get to a cell tower and your data that you're browsing on your browser also gets to the cell tower, they don't want to have to build two separate networks, one to carry your voice call and the other one to carry your data packets. They want to build one network. So they're going to build a packet-switched IP fiber network that goes to the tower and carries both. But wait a minute. They need the voice to look like this. They're okay if the data looks like this. How do they merge these two things together? They mark these packets differently with like a flag or something like that, a little bit that's set, and they use equipment that's running software that will prioritize the voice packets. They're not very big. They don't take very much. And your data packets really, some of them are going to look like this. They're going to be huge compared to the voice packets. So you can do it if you've got the equipment to make it happen. One way to do it is to make all the packets small, to break them up into small pieces. So there was a very popular technology, and there's a slide or two on it later, called asynchronous transfer mode, or ATM. Doesn't stand for automated teller machines, or not just automated teller machines. And all of its packets were 53 bytes, compared to 1,500 bytes, which is typical on the internet, 8,000 bytes, which is typical inside of a network, like U of H. So tiny, tiny, tiny packets. But the advantage was that it was very easy to regulate that. So in this diagram, each one has these things. Again, the behavior that you're trying to produce is that of a non-shared network, a dedicated point-to-point circuit. Okay, so that's the illusion. There are a couple of popular ways of dealing with circuit switching: FDM and TDM. Anybody want to take a guess what those stand for? If you've had EE stuff, you probably will have run into it. I'm always curious if you have, if you've run into it as a computer scientist. Sounds like nobody is anymore. So, our field kind of evolves and changes. It also depends on the school a little bit. This is frequency division multiplexing. And so what that does is take my frequencies that are available, like the colors in that big map that I brought last time, and allocate a different range of the frequencies available on your medium to different users. Well, that's clearly what we do with the wireless spectrum, but it's also what you do on a cable television network. That coax cable is capable of carrying lots of different frequency spectrum, so we're going to break it up into 3,000 hertz, 3,000 little notches basically, and assign a different television channel to each one. And so they're all transmitted simultaneously, but they stay out of each other's way. On a FM radio, we're going to broadcast all the stations at once, but they all stay within their little frequency, so they don't interfere with each other. And all you got to do is just tune into one. Just narrow the range you're listening to a very narrow one. If you expand it too wide, and your radio wouldn't do this for you anyway, but you can design one that does, then you'll hear a combination of all the signals at once. It wouldn't make any sense to you. Okay, so that's frequency division multiplexing. What are the pros and cons that you can see of an approach like this? Let me ask you some questions about it. Do you have to share the network with anyone else? Some people say yes, some people say no. Well, both are, you can argue both. So let me make the question more specific. For the frequency that you've been allocated, like the person that got this pink one down here, do they have to share their frequencies with anyone else? No, it's just them. Solid line over time, never gets thinner or thicker. It's just that solid pink bar all the way across. They can do whatever they want with that frequency, but the network is bigger than that. The network can handle lots of frequencies. So for radio stations, this makes sense because radio stations always generate the same amount of traffic per second. You know, even when they're like not saying anything at the moment, they're still transmitting. They're still, the electric meter is still spinning on the transmitter. So they're still paying for that. It's still their licenses. The problem comes in when you try to use this for things like the internet. Why? Yeah, because the reality with the internet is this pink bar probably needs to look like this. And typically the way we use the internet is short periods of lots of activity separated by long periods of almost none. So anybody know who Yogi Berra is? He's a very famous Yale baseball player, ended up being a player for the Yankees, I think, and then a very famous coach. But he's famous as much for his one-liners as anything else. So for example, one of his famous one-liners is, "We may not be the fastest team in baseball, but we are the slowest." So things like that. Baseball is 90% mental, the other half is physical. Right? One of the quotes that relates to this is, baseball is 20 minutes of excitement crammed into 2.5 hours. And so it's worth looking up. He had some good one-liners. So that's one way to do it. The other way to do it is time division multiplexing. So frequency division multiplexing has the problem that when you need more bandwidth, statistically, it's there because the other users are also doing something similar. Probably should draw that with a different color. So, and I'm trying to draw just kind of EKG sort of stuff. So what do you notice here? Both of these guys need it at the same time, but look, blue's got it to himself here, green himself, red himself. So if I could just borrow these other frequencies for a moment, I'll give them right back, I could get my transmission done a lot faster. So the problem with this is it forces everybody like into a modem telephone call. Remember modems? Anybody here ever used one? Those AOL Frisbee discs that you used to get in droves in the mail, and you have your phone, it would make those sounds. Does anybody here remember modems? Yeah, sort of. Hand goes up. You guys are really just trying to kill me here, aren't you? You're trying to make me feel old? All right, I'm going to torture you then. So we're going to play, here we go, MMP negotiation. I used to be good enough at doing this at the phone company that I could tell you what protocol you were running by listening to the negotiation. I used to be able to listen to touch tone tones and write down the number you were dialing. So be careful. Be careful. I have that gene. So let's see what it was. Anybody remember those sounds? They're like what fax machines make. So this is an MMP10 at 56K. That's a full channel 64K connection. Digital telephone system. That's me. That's amazing. So that was not a Ray Vedic one. Okay, so anyway, it's amazing the stupid stuff you remember. Sometimes I wonder, like, what useful thing in my brain got pushed out when I decided to remember that instead. So that's basically a frequency division multiplex network, because all the bandwidth you had was however much bandwidth the phone company had set aside to carry a human voice. So you could play those tones. The reason you can hear them is because they have to be in the same range as the human voice. That's what that network was designed to carry. So you spread these tones across, and if the network is good quality, you can put them closer together, and that's what was being negotiated there. Testing, sending all these tones, seeing which ones had strong signals, marking out the ones that didn't, And then on your computer, you would see, here's how many bits a second I can send. I'll spread them out over all these different tones. Each tone is a different frequency, and I will send ones and zeros over each one of them. And depending on the quality of the telephone network and its sampling rate, I can do more or less. But you're never going to get more than 64K because that's the number of times a second the phone network samples that line and encodes it in the first place. So you can't do more than that. You can do data compression, that helps push it up, etc. Okay, TDM is the other way to do it. This is time division multiplexing. So this is one where I'll sample your data, but I'm going to give you the whole network, but every once in a while. So you can have the whole thing if you want, but you're going to have to share it over time. So this is the way digital carrier networks like T1 networks work. We don't see this sort of scheme as often. One possible example might be some cable networks in some apartments, but generally speaking, these are not really used all that often. What we've done instead for the internet is we give the whole thing to one person. We hand them all the frequencies all the time. They buy, to connect routers together, you buy a dedicated point-to-point circuit that is not shared with anyone else. And it runs from my router to your router. It's shared heavily, but all that is dealt with inside the router. It builds its own buffers, it makes its own queues, it organizes the packets the way it wants, it decides who gets dropped. All that's done in software or a firmware implementation of it. And by the time it's here, it's just bits as fast as it can send them, and it's not sharing them with anyone else. Right? So don't get fooled into believing that just because it's the internet, that this is some packet switch type of circuit. It's the same 100-year-old piece of copper that we've always used. Copper did not change the way it behaves because of the internet. It's the same molecule, right? So lots of people sort of get lost in that detail. Okay, continuing on with this. So packet switching allows more users. It's shared, and the reason why it's what we do want to do with the internet is because we're not usually trying to implement lots of circuit switching. We are usually looking like these colors of these graphs. We use it a lot briefly, and then we don't do anything with it at all. How many packets is your network sending over the internet from home right now, for example? Not a lot. So counterintuitively, the more users you put on a core backbone circuit of a network, the less bandwidth per user you need. Let me say that a different way. So if I'm the phone company and I have a technology in the neighborhood with 1,000 users on it, and I've got something that's got to send it upstream to the rest of my network and on to the internet, there's a formula that says how much total bandwidth do I need to dedicate here to handle these 1,000 users. Now, they're not all 1,000 at home at the same time, and you may have started off with just 100 users here, and you may work your way up to 100,000 users later. Certainly, this is bigger than this one and that, but the ratio is the absolute smallest here. The amount of bandwidth per user is tiny compared to this and this. So it's counterintuitive. So it's great for the phone companies. It's great for the backbones of the internet, because the more users you have, the less bandwidth per user you need. Why is that possible? How does that make sense? Does that seem intuitive to you or confusing? So the reason why it works is because of this behavior down here. This behavior suggests that you're going to use it for sending something big for a moment, and then you're not going to use it much. So the less time I can make it take for you to get this done. If I can turn this into this, whoops, like almost no time at all to get it done, then you're done faster. You're on and off the network quickly. I can get a lot more of these packed together with lots of users in this same space it took one. So I can use the same amount of bandwidth per same total amount of data transmitted, I mean, per user. But because the network is much larger, which basically means its bandwidth is bigger, then you transmit much sooner. So you remember the simulator we looked at, right? You saw that with the simulator. When my network, wrong one, when my network looks like this, how many other people can be using this network right now? No one. When my network looks like this, or maybe like this, how many other people can be using the network? I could have lots more people right behind me, couldn't I? So the more users I have, I need a bigger network, but it doesn't scale. It's logarithmic or better even. Okay, guys, I think we're about done, right? So the class, I think, is scheduled to end at 9:50. Isn't that right? Okay. I'll give you guys a homework. You're going to have to kind of work through it. Here's what I'll tell you. If it's impossible to get the problem done, then don't do it. Try. But I want some evidence. So you'll see in the first homework, I want screen snapshots of things that you find. If you can't find it, and after 15 tries, all you see is can't get there, take a little screen snapshot of that and drop that into the homework instead. And I'll tell the TAs, that you guys may not be able to do some of those problems. Some of them you're absolutely going to be able to do, but with the shutdown, what can I say, right? I'm just hoping I can get on a plane today, and that TSA is there. So you've never seen so many people be so nice to TSA agents in your life. And this is not getting paid. It sucks. All right, see you guys back on WebEx on Thursday. So long.